Welcome to the video podcast series here at Ontario High School. We're dealing with acid-base fundamentals. This is part 6 of this series, and specifically today we're going to look at the acid-base properties of salt solutions. So, welcome. So, we need a rationale for this because we ought to have a rationale for just about everything we do. So, the acid-base properties of salt solutions are due to the behavior of their constituent cations and anions. These ions react with water to produce either H plus or H minus in the aqueous solution, and this process is called hydrolysis, and that's what we're going to take a look at. We're going to take a look at first the anions of weak acids, and you know that an anion is a negatively charged ion, sometimes monoatomic, oftentimes polyatomic. So the anions of strong binary acids such as HCl or HI, hydrochloric and hydriodic, they do not hydrolyze water, so there's no pH effect due to their presence in aqueous solution. But anions of weak acids, and for example here the acetate ion CH3COO- from acetic acid, which is a weak acid, CH3COOH, these do hydrolyze water, and when they do that they'll produce hydroxide ions in solution. The presence of excess hydroxide ions in solution will affect the pH, and rather than the solution being neutral, it will take on a basic quality. So let's take a look at how the acetate ion affects the pH. Here's the equation, the acetate ion when dissolved in water, and this can be present either through a salt such as sodium acetate being dissolved, or as the result of a neutralization reaction with acetic acid, where when you reach the equivalence point, there is only the acetate ion present. The acetate ion will react with water to form acetic acid and the hydroxide ion. Because it is a weak base, it will ionize the water, split off an H plus from it, and form the non-ionized acetic acid. And that's what you're seeing there. The hydroxide ion in the aqueous solution produced by the hydrolysis reaction will cause the pH to be basic, which means it's greater than 7. Well, the question begs to be asked, so what? Well, the so what of this is that we need to be able to calculate the pH of a solution in which the salt or conjugate base of a weak acid is present. So let's take a look. We're going to calculate the pH of an aqueous solution that is 0.1 moles per liter sodium acetate. And first we want to write the net ionic equation for the reaction, and we're not going to include the sodium ion because it's a spectator. And also note here, when I showed you the initial reaction on the previous slide, I included phases. Because of room requirements, the phases aren't here, but you should include phases in any of these equations. So we have the acetate ion, again reacting with water to form non-ionized acetic acid and the hydroxide ion. Next we want to calculate the base equilibrium constant for the acetate ion. We know that Ka for acetic acid is 1.8 times 10 to the negative fifth. We also know that Kw, which is the equilibrium constant for water, is 1 times 10 to the negative 14th, and we know that Kw is always equal to the product of Ka times Kb. So we're going to rearrange the equation to solve for Kb. We'll put Kw on top divided by Ka, so 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative fifth gives us a K sub B of 5.6 times 10 to the negative 10th. Well, we have the net ionic equation for the reaction written, and we have the equilibrium constant for the base, the acetate ion. So next we're going to use an ice chart and the equilibrium expression to find the hydroxide ion concentration and the pOH. So here's our ice chart. We initially start with 0.1 mole per liter of the acetate ion. The water's irrelevant, so we'll just put a dashed line there. And we're going to assume that we have 0 of the acetic acid or hydroxide ion at the beginning here. The change is going to be minus X for the acetate ion, plus X for each of the acetic acid and hydroxide ion concentrations. So at equilibrium, the acetate ion concentration will be 0.1 minus X, and then the acetic acid and hydroxide ion concentrations will be X and X. Now, K sub B is very, very small, 5.6 times 10 to the negative 10th. So we can use our rule where we take the K sub B, divide it by the 0.1 original concentration of the acetate ion, and then multiply that by 100. And if it's less than 1%, we can ignore X and take 0.1 minus X to be more or less equal to 0.1 mole per liter, because X is going to be so very, very small that when we apply significant figures to this 0.1 minus X, it will still round to 0.1. So we set up our equilibrium constant expression, 5.6 times 10 to the negative 10th, is equal to the concentration of acetic acid, CH3COOH, times the concentration of hydroxide ion, OH minus, divided by the concentration of the acetate ion, which is CH3COO minus. We plug in our numbers from our ice chart, so it will be X times X on top divided by 0.1, and we can simplify that to X squared divided by 0.1. So X is equal to the hydroxide ion concentration, which is what's going to affect our pH, so that's what we're interested in solving. And that's going to be equal to the square root of the product of Kb times the concentration of the acetate ion. So the square root of the product of 5.6 times 10 to the negative 10th times 0.1 gives us a hydroxide ion concentration of 7.45 times 10 to the negative 6 moles per liter. Now, we can't find pH directly, but we can find it rather easily if we know our pOH. So our pOH is going to be the negative log of the hydroxide ion concentration, and the negative log of 7.45 times 10 to the negative 6 is 5.13. Now that we have the pOH, we can easily find the pH by subtracting pOH from 14. Remember that pH plus pOH is equal to 14. So 14 minus the pOH of 5.13 gives us 8.87. So our pH of the 0.1 mole per liter acetate ion solution is slightly basic at 8.87. Well, we just calculated the pH of a solution that contains a basic salt, a conjugate base of a weak acid. So let's look at calculating a pH of an acidic salt, the conjugate acid of a weak base. The weak base we're going to use is pyridine, which is C5H5N, and its conjugate acid is C5H5NH+. We're going to determine the pH of a 0.1 mole per liter solution of that. So first I want to write the equation for the reaction. So I have my C5H5NH+, aqueous, plus H2O liquid will yield C5H5N plus H3O+. And it's that concentration of H3O+ that's going to be the determinant of the pH of this solution. One of the things that you're going to notice is that this conjugate acid of pyridine is a proton donor. It's going to donate H+ to water, and that's what's going to be responsible for this. First, we want to find Ka for C5H5NH+. Using the same principle that we did before, Kw is equal to Ka times Kb. So Ka is going to equal Kw divided by Kb, 1 times 10 to the negative 14th, divided by 1.7 times 10 to the negative 9th, gives us a Ka for C5H5NH+ of 5.9 times 10 to the negative 6th. Now that we have the Ka value for C5H5NH+, we'll go ahead and use the ice chart and the Ka equilibrium expression to find the H3O+, which we know as the hydronium ion, and the pH. So here's our ice chart. We are starting out initially with 0.1 mole per liter of our C5NH+. Water, again, is not part of the equilibrium expression because it's a pure liquid. And then the initial amounts of pyridine, C5H5N, and H3O plus are 0. Our change will be minus X for the C5H5NH plus and plus X for the pyridine and the hydronium ion. At equilibrium, the C5H5NH plus concentration will be 0.1 minus X, and then X and X for C5H5N, the pyridine, and H3O plus, the hydronium ion. Now, we apply the same thing that we did before to see if we can drop X out of that expression 0.1 minus X and simplify this so we don't have to use a quadratic. So we take 5.9 times 10 to the negative 6, divide it by the 0.1 mole per liter concentration to start for the C5H5NH plus. Then we multiply that by 100, and it's way less than 1%, so we can drop that out and make the equilibrium concentration of C5H5NH plus 0.1 mole per liter. So let's go ahead and set up our equilibrium expression. 5.9 times 10 to the negative 6, the Ka of C5H5NH plus, is equal to the concentration of pyridine, C5H5N, times the concentration of the hydronium ion, H3O plus, divided by the concentration of the C5H5NH plus. We put in our values from the ice chart, so it'll be X times X on top divided by 0.1, which we simplify to X squared divided by 0.1. Our X is equal to the concentration of our H3O plus, and so we're going to take the square root of the product of our Ka value times the initial concentration of the C5H5NH plus. So 5.9 times 10 to the negative 6 times 0.1, the square root of that product gives us a concentration of hydronium ion, H3O plus, of 7.7 times 10 to the negative 4th moles per liter. pH is equal to the negative log of the hydronium ion concentration, so it's equal to the negative log of 7.7 times 10 to the negative 4th, which is a pH of 3.11. So here we have the conjugate acid of a weak base present in solution, causing the pH of the solution to be acidic. Here are some undeniable truths. How's that? Number one, an anion that is the conjugate base of a strong acid, for example, Cl- is the conjugate base of HCl, meaning the chloride ion is the conjugate base of hydrochloric acid, will not affect the pH of a solution. Number two, an anion that is the conjugate base of a weak acid, for example, F- or the fluoride ion, which is the conjugate base of the weak acid hydrofluoric acid, will cause an increase in pH. Undeniable truth number three, a cation that is the conjugate acid of a weak base, for example, the ammonium ion, which is the NH4 plus is the conjugate acid of ammonia, NH3, will cause a decrease in pH. And finally, our fourth undeniable truth, there are several more in the next podcast, so be sure and tune into that, but is this: when a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the ion with the larger equilibrium constant, Ka or Kb, will have the greater influence on the pH. Well, we've come to the end of part 6 of the acid-base fundamentals. In this one, we dealt with the acidic and basic qualities of salts, or the conjugate acids and bases of weak acids and bases when they're present in solution. So, as far as the end goes, it's not bad. There is another podcast coming that will deal with the influence of metal cations on the acidic behavior of a solution. You'll want to watch that one. There's more undeniable truth awaiting. I want to leave you with a quote from Miguel de Cervantes: "Fair and softly goes far." I wish you well.